welcome to the fourth workshop. Here I've got the attendance form on the left and my notes on the right. So you can just feel free to scan those QR codes. So today, the topic, just realized this is workshop 3. So the topic today is going to be on trusses. So you've probably had your lab this week where you focus on modeling a truss. And yeah, you've seen that it's a little bit different to how a beam works, but I'll explain in more detail how they work. And we're going to do some questions with them, and I'll show you 2 different methods you can use to solve a truss and its internal forces in the members. As usual, we'll have our quiz and our break, but I'm forecasting this workshop to be a bit shorter than last time, so you'll be able to leave before 6 o'clock on the dot. Just another fun fact about this topic is that this is the 3rd workshop that they have when you do this course in the mech school or in the mining school. So they put trusses before beams, but in civil we do beams before trusses. It doesn't really matter as long as you learn both, because both the beams and the trusses will be in your midterm, which will be next week. So for your midterm, just keep in mind that one's actually like mandatory attendance to get the marks. So you want to be in next week. And Waze said that we started at 5 and give you 50 minutes to do it. But if everyone's there and they want to get home a bit earlier, I'm happy to start the midterm a bit earlier and give you the same amount of time to finish it. So yeah, basically that's how I'll work next week. Bear with me for a second. I'm gonna pull out my notes. Yep, and for anyone who wants the recordings, that's there as well. The recordings of the workshops. So this workshop will also be recorded, of course. Okay. Without further ado, we'll move on. In terms of where we're at for the course, we've covered the beams and frames. Oh, I haven't updated this, sorry. This week will be on trusses, basically. So we're just covering that topic, right? And we're still in statics, and this will be pretty much the last topic that we're going to be covering before we touch on dynamics. Technically, frames are a part of the statics portion of the course, but you won't be assessed on any frames for your midterm. Frames will come potentially at the end of the course for your finals. So just keep in mind, it can get a bit harder in terms of statics, but not until the finals, right? Does anyone have any questions about course structure or anything like that? Okay, so let's talk about the difference between these kind of structures that I've been alluding to, right? So previously we've been looking at frame elements, namely we've been looking at beams, which are the horizontal members designed to take on like bending moments, shear force, these kind of things, and we've been graphing them. So last workshop we graphed it to show us the shear force diagram, bending moment diagram, which by the way, you can expect to have to graph shear force diagrams and bending moment diagrams in your midterm. So you want to learn those methods pretty well. I don't want to make promises, but from what I've seen in the midterm, with the shear force and bending moment diagrams, you can graph them in any way that will get you the key values. So generally you can get away with the faster method, which is the graphical method, as long as there's no triangularly distributed loads, which you won't be able to find the key values using the fast method for. And typically Waze is pretty nice. He probably won't give you a triangle or a trapezoidally distributed loads until potentially the finals, right? So this midterm should just be dealing with uniformly distributed loads on beams and point loads on beams, right? And so with these frames, you can see in the corners of where the columns and the beams are connected. Typically beams and columns are joined at right angles like this. And this is what we call a rigid connection, where if it's 90 degrees or right angle from each other, they stay at 90 degrees or right angle from each other, even when there's loads on it which cause it to bend. They're rigidly connected, so they aren't free to rotate relative to each other. On the other hand, we have trusses, where we have all. Oh, sorry. Give me a moment. I realize I'm drawing over my master document. Okay, sorry about that. So yeah, basically with trusses, the joints are all pinned, right? So here I like to draw them with circles, but during your diagrams, as long as people are clear that you're talking about a truss, you don't technically need to draw these circles for it to be like accurate. It's from implication. But the idea is all of these joints are free to rotate, like your elbow or like your knee or whatever. That's like free to rotate, essentially, right? Yep, and in terms of connections, right, that pinned connection is also sometimes called a hinge or a simple connection, right? So that's terminology which you might hear. And let's talk about rigid connections. Yeah, so rigid connections is what we saw in the frame, but they can also apply for certain machines which have this kind of connection which don't move relative to each other, right? There is technically also a roller connection, which looks something like this, but I've never seen it in the civil stream of 1300. And they pretty much only apply for machines, for mech, and there's kind of like ball and socket joint, right? Okay, does anyone have any questions to do this so far? Okay, so other common terminology which you'll hear is like simply supported beam, which I think I've mentioned in one of the earlier workshops. And we want to start thinking about, okay, basically all of the structures you're gonna find in this course are what we call statically determinate. And there's enough unknowns and equations to solve them, right? So we use our equations of equilibriums to solve out for our unknown reactions, right? Another type of structure we see is called a cantilever beam, and that's where you have a fixed end, right, which has that resistance in bending moment, that, as well as our translational restraints, right? And the other end is like a free end, right? So these are the two quite simple and common types of structures that we see. To be honest, I wrote these notes for summer and it was in week 3, but I think I already explained it because I explained it in the beams portion. So anyway, I might have just doubled up on explanation, but let's talk more about trusses, okay? So another thing about trusses, aside from the fact that the joints are all pinned, is that forces and the point forces, specifically point forces, are only applied at the joints, right? So you're never going to see any shear forces, which are like the perpendicular loads acting along the member of the beam, and you're never going to see distributed loads acting on the truss, because then it's not a truss anymore. Then you have shear forces, and you have bending moments, and the truss members aren't designed to take on these kind of loads. They're designed to only take on axial loads. So we call these members two-force members because they're only able to take on tension and compression, right? Does that make sense to everyone and the terminology? Another thing you might want to consider is the reactions are also technically just forces acting at joints, right? But in the form of support reactions. So it's still, I guess like, yeah, that assumption still applies for the support reactions, right? Okay. So now we're going to talk about zero force trust members, right? So this is probably something you haven't really discussed in the lab or in, oh, actually, I think Wei might have talked about it in the lecture briefly, but zero force trust members is basically when a trust member has zero tension and zero compression, right? Zero force. And there's ways which you can identify it, and specifically there's two cases that you can use to identify it. And sometimes this will save you a lot of calcs, not a lot of calcs, but it can save you time in your calculations, right? And sometimes it can, actually, it's pretty much just for saving time. Yeah, I'll just leave it at that. I'll give you an example of how it can save you a lot of time in a moment. But yeah, I'll explain the cases first. So in the case that two members meet without any external loads happening at that joint, so we're looking at a joint by joint, by the way. Yeah, if there's no external loads happening at that joint, then both of these members connected to that joint are going to be zero force members. That's the first rule. The second rule is if there's three members meeting without any external loads and two of them are collinear, which means two of them follow the same line of action, right? The non-collinear one is going to be a zero force member. Those are the two rules you're going to have to memorize for this simplification, right? So let me show you just how much you can simplify this truss, right? Okay. So say we have a truss that looks like this, right? Okay, so we have a truss that looks like this, and we have a point load acting at the node that's the furthest away from the supports, right? Okay, so we can look joint by joint at, to see if we have any zero force members. So this one it doesn't meet any of the conditions straight away because we have three members and none of them are collinear, right? And we also have these reactions as well, so that wouldn't work either, right? So as soon as there's a point load or a reaction, straight away it can't be zero force. Can't be zero force members attached to it, right? And then here we have a point load, so that doesn't apply either. Okay, so we can look joint by joint. This one has 4 members attached, 4 members attached, 4 members attached, 4 members attached, okay. But then here, we reach this point where we then have 3 members attached and 2 of them are collinear, and there's no point loads acting at that node, right? So what this allows us to do is consider that as a zero force member, right? And now, okay, great. So that saved us a little bit of work, right? Just one zero force member. But it's an iterative process because now we have to scan all the nodes again to see if we have any zero force members after we eliminate that one. So you'll go through the same process again and check all the nodes. Once you reach this one, you can effectively not look at that one, right? Now we have a node where there's 3 members, 2 of them are collinear, and 1's not collinear, and there's no point forces. So we do the same thing, and we can wipe out that one in terms of our analysis, right? And we do the same thing, wiping out these members, right? Until we're left with a truss with effectively 3 members that we can easily calculate. So we simplified it down from an 11-member truss to a 3-member truss. And I mean, Wei's never going to give you this question, but I suppose like in some universities, for professors who are quite nasty, they could give you this question in a test and it's a complete debate as to whether you know how zero force members works, because either you're going to be sitting there for 200 years doing the overall truss, or you're going to know the simplification and do it in like 1 minute, right? Okay, does anyone have any questions to do with this? One common question which I get when I show people this example is, okay, well, if these are all zero force members, right, if I just redraw them, if these are all zero force members, then why do we even have them there? Like, what's even the point, right? So that's a good question because basically there's a few reasons. It's actually quite a loaded question. So, firstly, what if this member snapped? Now all of these members aren't going to be zero force, right? Oh, actually, sorry, that's a bad example because it's still zero force. Okay, what if this member snapped, right? Now these are going to do something. Firstly, in terms of the axial forces, but secondly, these are going to add rigidity so that the deformations aren't going to be as high, which you'll learn about more in solid mechanics, but it's not part of the scope of this course. But yeah, so that's a question I've gotten a few times. Okay, everyone okay with this? Happy to move on? Cool. Okay, so let me explain to you the two methods we use to solve trusses. I'll let you absorb this and I'll turn off the lights. So there's a lot on the screen right now, and I'm gonna slowly explain it, right? So firstly, step 0, identify and remove any zero force members. So you don't need to consider it in your analysis, okay? Okay, step 2, find the support reactions using equations of equilibrium, right? But this is with an asterisk, because you'll see in one of the later questions, unless the question specifically asks you for the trusses support reactions, you don't always need to have the support reactions to solve trusses. And that's like a little trick they can do. So for beams and shear force diagrams, bending moment diagrams, you always need to solve for support reactions before you can fully solve those graphs, right? But for trusses, sometimes you can avoid doing it. So you'll see in one of the questions later how that applies. Okay, so now we can choose either the method of joints or the method of sections, which I'll just show you through the actual questions. It's easier than explaining it theoretically, right? And in method of joints, we analyze everything joint by joints, right? So, it's going to look something like this, right? We're going to only look at the free body diagram at joint A. And if you remember, in our first topic, right? Sorry, I'm going to actually go back to our first topic. Every single one of these questions have been in something we call particle equilibrium, right? Because in this first topic, they have only taught you guys about forces, but they haven't taught you bending moments yet, right? So all of the forces will meet at a single point. And since all of the forces meet at a single point, it's what we call particle equilibrium, and no moments are causing our particle to spin or do anything weird, okay? So if we go back to my workshop 4, when we analyze a single joint, all of the forces will be concentrated at this single point. And so we can't use the sum of the moments formula anymore. We only use the vertical force equilibrium and the horizontal force equilibrium, right? This method results in a very slow process where you slowly work your way through the joints until you get to the ones of interest, right? And you usually work outside in. That sounds a bit abstract right now. But if we have a truss that looks like this, for example, we usually start from somewhere we have a lot of information, like say we solve that support reaction, and we work to the adjacent joints and work our way through like that. So outside in, that's kind of the process, okay? The second method is called the method of sections, right? And this method is a way to find certain members quickly. But it's pretty fast to set up if we only want, say, 2 or 3 members' internal forces, but it's not an efficient way of getting all of the members, right? What this involves, I might draw a bigger truss. So we have a bigger truss like this, right? And we're only interested in this member, and this member. What we can do is we can be like, okay, let's just take a cut across that area and only analyze the free body diagram to the left. This exposes the internal forces inside those truss members we cut across, and we can disregard everything else other than what we can see. That's what the method of sections involves. And yeah. Okay, sorry. I know I just said I'll explain the practically instead of theoretically, but then I just started diving into explaining it theoretically. That might all sound very abstract at the moment, but what I'll do is I'll give you guys the quiz, so you guys can. The quiz is mainly focused on zero force members, so you can identify those zero force members, get the foundational skills, and then give you a break, and then we'll work through some questions where the method of joints, method of sections will hopefully make more sense, right? Okay, so it's time to grab out your phones. All right. Yeah. Anyway, this one. Is anyone still signing in? I'll give it a few more seconds. Okay, is that everyone? Okay, I'm gonna assume everyone's in now, right? Yes. Okay, have fun. Jared. Very good. Okay. Oh, it's 50%. Excellent. It's shifting up, isn't it? But yeah, look, if you're feeling stressed for the midterm, it's good character development. So it's only going to get harder in engineering. No, I'm kidding. That's kind of toxic. I'm joking. All right. Okay. So where are the zero force members? Very good. There's no zero force members. So if you look at A, if I zoom in here, A actually has 3 members connected to it, and there's no 2 collinear ones, so it's not zero force. And this was probably quite a difficult question because there's a lot to consider here. Firstly, if we look at node G, right, we have that case of 2 members being connected to it, right, and no external point load. And so in that case, we have the whole, both GE and GH are going to be zero force. Over here in I is going to be 3 members connected to it, and 2 of them are collinear, and there's no point load on it, so IJ will be the zero force. Similar situation for CD being zero force. And for member JL, for those of you who thought JL was zero force, again, we do our analysis node by node, right? And so we can look at this node for when we're talking about whether this member is zero force, or we can look at this node. So at this node, there's 5 members connecting it, so there's 0 chance that's zero force on that side, but it could still be zero force based on this node, right? But it looks similar to the node G, but because there's point loads acting at that node, it can't be zero force. Okay. Let's move to the next one. Okay, so this is a bit about beams, right? And you have to keep in mind when we look at the external loading happening here. So if you haven't recognized it already, the last question was your lab question, and then, or like lab assignment question, and this one's also a lab assignment question. Or maybe they slightly changed it. This could have been the 2023 one. But anyway, so basically all of these forces which are happening on this beam are perpendicular to the beam's main axis. The beam's main axis being like this way. And so there's no axial forces because everything's strictly perpendicular, right? So yeah, no axial force. I feel like this one was quite a disagreed upon answer. Is anyone like confused about that? Yeah.
Those 2 forces diagonal, so they're x components.
Oh yeah, okay, sorry. This is to do with the stupid notation. So I see what you mean. Yeah, I see what you mean.
Pointing to all those.
Yeah, basically, yeah, no, I know what you mean, but for everyone else who was confused, right? Yeah, no, that's a really good point, man. So this is a point load, and there was like some other distributed, whatever, right? In both the assignment and in the midterm, you're gonna have to get familiar with the fact that the free body diagrams might have arrows pointing at distributed loads, right? So it's gonna say like this is like 5 kilonewtons. It's saying this arrow refers to the fact this distributed load is 5 kilonewtons. It'll say kilonewtons per meter, right? It's not a diagonal point load. Yeah, it's quite stupid. Yeah, I reckon as well. Yeah. So what I do in my notes is I usually do it like that, squiggly line. There's no confusion if it's a squiggly line instead of an arrow, right? You know what I mean? So yeah. No, good point though. Please, like, don't make that mistake in your midterm. I have a bet going on with the other tutor, Lockie, in the other room, that if we get more HD ratios in this class, I get $5, and vice versa if he gets more in this. Anyway. Oh, sorry, I don't know why I did that. Try to pull this up. Okay, yeah, so don't confuse those, yeah? Okay. And then this one is, again, it comes with a bit of practice, but you can kind of identify which support reaction is bigger based on vibes. So essentially, this support on the left, right, is kind of in the middle of the beam, and it's going to take on more of the forces, including more of this force from this one over here. Whereas this one's off to the side, so it doesn't have to contribute as much of the reaction here. We'll talk about the vertical forces. Right. So this is a sanity check. So in your midterm, again, if you run into a situation where you calculated this and your vertical reaction at C is bigger, you fucked up, basically. Like, yeah. And you won't even know that because to get the second vertical reaction, you're going to take the sum of the forces and it's going to appear to be right because both of those forces, By and Cy, are going to equal the downwards load. It's going to appear to be right, but you did something wrong in your sum of the moments calculation, if that's the case. So yeah, just have a good intuitive understanding of how these reaction numbers will work, right? Okay, I'll give you guys your break, and we'll come back at 4:45. Or 4:45.
I see how like a yeah, no, it's just relative fairly different. I would notice it, but it's like yeah, it's like it's just past papers, but the form is such a change. Just the numbers change. Yeah. And then they got a good explanation. Well, it's just got the work. It's got the working again. Yeah. Good explanation. I haven't watched it. No, yeah, you can't speak. That's right, but not
I reckon the weekly quizzes are harder.
I got like 16% for the last one. I'm not stupid. Like I never knew it. I was just balancing out the X and Y components.
Yeah.
No, I didn't want to attempt. I was like, I need to do it again. It's like I honestly don't know. It was just like it was like a trust. I just had to balance out the X and Y components. It's like I knew exactly what to do. I just I don't know.
The first one is pure.
Yeah. It's a good yeah, and then the next one, I just put in ChatGPT, gets it right. So you could, I was looking at a trust calculator. Yeah, but apparently it wasn't a trust, that was what Ray was saying, it wasn't technically a trust. Yeah, it was a fake trust. No, like that, you do the grade one. I was like, how do I do that? I think I put in ChatGPT and did it. I was like, yeah, sweet. It actually worked for it. Yeah, photos. They updated it. The free version got updated.
Oh, really?
Yeah, but you get like three. You can upload 3 pictures a day.
That's not bad.
That's actually so good.
Three subjects.
Yeah, yeah. Get onto it. Yeah, I don't use China. It's actually online. Yeah, but it's
helpful, but then it kind of feels like
No, but like not for like changing purposes, just like in general, like just like
it gives you a good explanation for what to do.
But it's not. It's wrong.
She's pretty intelligent.
Yeah.
So if you just put it in there, then you get like
Yeah.
that's kind of just
But if like you look at the answer, you can put yourself and like help.
Oh yeah, I can do that. I make do it again.
Yeah. That's so true. You go into it thinking like, yeah, I'll do it myself, like I'll get the solution, but then like you see, like it's
Yeah, look, I did everything I've done. Go to see my book.
If it's like a clear explanation, like a clear description of the question, it doesn't respond to that. But if it's like already a explanation,
Okay.
and the trust calculates.
Yeah. Okay. Sorry, I cut your break off a little short. Basically, I just want to quickly talk about something because I was supposed to talk about this at the start. And yeah. I'd just like to promote a little opportunity for you guys. So, has anyone heard of Engineers Without Borders? So, Engineers Without Borders is like a interdisciplinary engineering society, and they focus on something called humanitarian engineering. So that interdisciplinary meaning like they get environmental engineers, civil engineers, mechanical, aerospace, and they have like a bunch of humanitarian focused like objectives. So they do a lot of work overseas with like water treatment, things like that. But the EWB branch, there's a bunch at different unis. The one at UNSW specializes in what we call youth outreach. So it's honestly quite wholesome. So what they do is they educate people, like students, usually like primary school to high school, on engineering and how it can better the world. And so they have this event that runs twice a year, one in the autumn and one in the spring, called Regioneering. And Regioneering is a really good opportunity, and it's free, and you just apply, and it's a week-long trip in the holidays, which you sign up for, and you go around to a bunch of different schools and teach the kids about these kind of engineering-based like learning modules and how they could firstly like aspire to become engineers and how that the engineering that they do can better the world and stuff like that, right? So I've included a QR code. This is a little bit of a this is like a premature cover photo because we haven't launched this event like technically online yet, but they gave me permission to show it early. So that QR code, obviously, it's going to link to a Google form, but you guys are seeing it before it's been publicly kind of released, I guess. So yeah, I would highly recommend this opportunity if you're interested in any of what I just said. Okay. So, sorry, I overheard something from what this table was talking about during the break. You guys were talking about the weekly, right? You guys might have been a little confused about that, and to be honest, part of that could have been on me because I didn't fully explain, like, I haven't been working through what the other tutors have been working through, which is like the civil questions. So those focus a lot on frames and stuff like that, machines. But there's a reason I don't do it, and it's because it's not in your midterm, right? But it is in your weekly randomly. So, and it's pretty much not in your finals, right? I can guarantee you there's no machines in your finals. So when in that first question, this is the first question, right? Not the second. Yeah. You can see this truss kind of prematurely before we teach you trusses properly, but we only care about the support reactions on the truss. So essentially, we don't need to know any of our truss methods. We just need to know that this is some sort of structure, and we can take the sum of the moments and some of the forces and work out what those reactions and stuff are here, right? You know what I mean? Yeah. Okay. Oh, and by the way, the arbitrary distance b gets cancelled out when you take the sum of the moments. So that's the trick with that question, I guess, right? The other question was to do with the crane, right? The crane is actually a machine, right? And it was in the last like 2 minutes of what I was talking about last week, essentially. It's the fact that machines have these pin joints, right? Like for example, here's a pin joint. And it can, what do you call it? Basically, you can split up the free body diagram by the pin joints. So we can look at just this part. We call it free body diagram A to D, and the free body diagram here from B to C. And there's a few other tricks here. I'll upload this to the Google Drive folder as well, so you can have a better look at it. But we have stuff like center of gravity, da-da-da. But the main trick is the fact that we can split it up by that joint, and then just assume that we have some sort of force acting through it, like that, which we can work out. That's the whole idea, right? Okay, and we don't need to even work out what the pin support reactions are, because when we take the sum of the moments about here, the lever arms will be 0, and so yeah, you just have one unknown basically. It's a really specific question that's not going to come up in a midterm, but I can drop it in the drive anyway if you like. Okay, let's continue with our actual workshop on trusses. So here's our first question, and I've chosen to give a fairly big truss because there's a lot of simplifications we can make here, and it shows, I don't know what it shows. It shows a lot of concepts. Oh. So sometimes the handle doesn't twist, so that you can just push it open. Okay. So, yeah, here it says neglect any horizontal reactions to the support. That's going to help us because we have 2 pin supports instead of a pin support and a roller, right? Essentially, what we're aiming to do is find out what the axial forces are in each of these members. That's what this is telling us to do, right? So when it says calculate the forces of each member in the truss, it wants us to do method of joints. Because as I briefly mentioned earlier, a method of joints is better for slowly working your way through all the members, right? But method of sections is better when they're asking you for specific members and the axial forces, yeah. Okay, so here's what we're looking like for, like, in terms of all the geometry. I've just redrawn it in terms of a free body diagram. We have reactions at A and at E, and point loads at a bunch of these top nodes, right? Okay, so essentially we start with our reactions, okay? So just like normal, we can take the sum of the reactions at A or E. Too lazy to do the maths, so I'm just gonna pull up. This is on my phone. One sec. Yep. Okay. So we have to account for essentially these three, the 2 reactions and that point load acting down. They have 0 moment because the lever arm is 0 around point A, right? So we just have to consider the load at B, the load at C, the load at D, and the load that point load 1 kilonewton and the EY reaction, right? This one will have a lever arm of 0 as well, right? Are we all still familiar with how that stuff works? Okay, so I'm going to quickly undo all that. So essentially, because they're all going clockwise, except for EY, they're going to be subtracting, right? So we go subtract 1 kilonewton, and it's 2 meters away. Subtract 1 kilonewton is 4 meters away. Subtract 1 kilonewton is 6 meters away. Subtract 1 kilonewton is 8 meters away. And then add on EY, which is our unknown we're solving for, and it's 8 meters away, right? So we move all of these onto the other side and divide by 8. And we get that EY is 2.5 kilonewtons. Okay. So we can take the sum of the forces, right? And yeah, I'll just do that. I won't be lazy. And you know, it's like EY, which goes up, AY which goes up, and you have 5 lots of your 1 kilonewton load, right? So basically, AY is also 2.5. But why I'm saying that you could have done that the lazy way is that this truss is symmetrical, right? So the support reaction at A and E should give you the same number because the loading is symmetrical, the shape is symmetrical, etc. Right? So you could have just done that based on vibes, basically, right? Okay. The other thing is that we're told in the question, neglect any horizontal reactions at the support. So actually, you don't even need to do that. So EX is equal to E, AX is equal to 0 kilonewtons, and that information is just given, right? Yeah, cool. We all following so far? So that's support reactions again. We're doing it for this question, but we don't have to do it for every question. And you'll get a better sense of that once I show you question 2 and question 3. Okay. Oh, I've even neglected my flow chart. Are there any zero force members in this truss? Yes? No? CH? DC? GC? Very good. So that's zero force. Because at this node, we have 2 collinear and 1 non-collinear no forces. So GC is zero force, right? You got a question? Yeah, so we do our analysis of zero force members node by node. So if on one end it's got like a billion truss members connected to it, it can still be a zero force member if on the other end it satisfies that criteria. Nope. Because it would be if there wasn't a 1 kilonewton load acting on it. Yeah. And also, if there was 1 kilonewton load acting at the bottom pulling this truss down, then this member wouldn't be zero force either, right? Yeah. Okay. The other thing to note is we mentioned that this was symmetrical, right? And so we're really only going to have to calculate half of these because due to symmetry, AB is going to be the same as, what does that say? I guess E. DE, right? And then, BC is the same as CD. You get it, right? So whatever's here is going to equal whatever's there, right? Okay. So now we've identified zero force members, we've identified symmetry, we've done our support reactions, we're ready to launch into the method of joints. How do we do the method of joints? Well, first we have to pick a joint to start at. So basically, let's just consider the left side here because of symmetry. It's advisable to generally start outside in because you'll have more information. So, how do I explain this? We wouldn't start at B because, actually, you know what, I'll just spill the beans. We start at A, basically, right? So, there's really not much confusion about it in this question, but in some questions, you have to think about it a bit more. We'll see if that pops up in question 2 or 3. You start outside in. So in this case, this is like, where we have our known information about the support reaction, and we're going to have 2 unknowns like this. So let's take a cut of this and analyze it down below. It looks something like this, right? So this is a 1 kilonewton point load acting down, and we have our reaction that's going up. So in terms of all our external loading and that information, we keep it pointing in the same direction that we've seen it, right, on the free body diagram. So, 2.5 up, 1 down, sure. Now, we have to, similar to support reactions, we just have to assume a direction and roll with it, right? And for, here's the way that I would recommend you do it for method of joints and even method of sections. Assume that your truss member is in tension, okay? So pointing away from the node. So assume that it's in tension, And if you get a negative number, it's actually in compression. And stick with that system throughout, right? And even if it's in compression, keep it as a negative number. Otherwise, you're going to start flipping double negatives and making mistakes. I'll show you what I mean as we keep going through this question, yeah? Okay. Firstly, we don't know this angle, right? So that's this angle here. So it's going to be difficult to do like sine, cosine for this diagonal member because we don't know that angle right now. So let's look at our geometry. Essentially, we have rise over run here. So you can either do that rise over run or that rise over run. It's going to give you the exact same angle, right? So the rule is tan inverse rise over run. The rise is 1 meter, and the run is 2 meters. So that's 1 meter, 2 meters. Yeah. Correct. Okay. If you punch that on your calculator, it'll give you 26.565 degrees, right? And we're going to have to keep this number in mind for a lot of the steps moving forward. But that angle is going to be 25. So say 25, I'm at 26.5. 6.5. Okay, so the question is now, similar to in workshop 1 when we looked at that that spike going in the wall and we had the 2 ropes coming off of it, right? You can either take the sum of the forces in the x direction or the y direction, but one of them is going to give you too many unknowns to solve, okay? We're in particle equilibrium. These are the kind of choices we want to think about, right? So have a think about it. Are we going to take the sum of the y forces or the x forces first? Why's that? Sorry? You're right, but why is that, do you reckon?
Eventually the forces cancel out.
Yes. Okay. Yeah. Yep. Exactly. So AB, we're only going to look at that vertical component of AB, and AH doesn't have a vertical component, right? So that's going to only result in one unknown. So if we do the x direction, we're going to get AB and that right component of it, and AH, that right component of it. So it's not going to work, essentially, right? So we do the -1 point load going down, the reaction going up, and now we just consider the vertical component of AB, right, which is AB multiplied by sine 26.565, right? Okay, and are you guys familiar with how to solve this on the calculator? You move this stuff to the other side, and then you can divide by the sine, like angle, right? And that gives you AB is equal to this, right? So, is this member in tension or compression? Compression, very good. So if you get a negative number and you use this kind of tension convention, then a negative number will give you a compression member, okay? So that's in compression. Okay, so now that we know AB, we can also solve for AH. Yeah, so I'm going to slow down after I write this line. So what I've done is, because my arrow is going to the right, I'm still going to add on AB and that horizontal component. That's where I'm saying with the double negatives, keep that direction of the arrow consistent. Otherwise, you're going to start tripping yourself up. What you need to do to account for the negative compression magnitude is when you sub in this number, plug in that negative number, and you'll get the right number. I said number like 3 times, but yeah, you get the idea, right? Now, when we solve for AH, right, you get AH is 3 kilonewtons, and that's going to be positive, so that'll be in tension, right? Is everyone following so far? We've done one joint, but 2 members. So Bear with me. Next, let's have a look at it again. We're at joint B. So basically, when I say we work inwards, right, where would it make more sense to work inwards from? I know I already showed you which joint, but can anyone explain why I decided to go to B? We also found AH. So, sorry?
Less members of that.
Very good. So the fact that there's less members will be a good hint that there's going to be less unknowns as well, right? And therefore, you'll have enough information to solve it at that joint. So we're going to move from A to B, not A to H. Otherwise, you're going to get stuck. Too many unknowns, right? Yeah. I mean, if you did go it that way, you could... Actually, no. Yeah, too many unknowns. Okay, so A to B. So now we're at B, and that angle stays consistent, that alpha value of 26.565, right? And we do the same thing. Okay, hold on. Yeah. Basically, just keep in mind, this is a solved number, right? Okay, so we take the sum of the forces in the x direction this time. Again, you make that logical decision based on how many unknowns there are. So if we took the y this time, you'll find that you have 2 unknowns. But if you take the x, you'll only have this one unknown. Okay. So cosine this angle, right? We're taking the horizontal forces, so we take the adjacent side, right, of this right angle triangle. Yeah. Okay, and then minus this AB. Again, we choose the negative sign here because the arrow is pointing to the left, right? So AB cosine 26.565, right? And now when we sub in the value for AB, which is in compression, we also put in another negative, right? That's what I mean by double negatives, right? But you will never trip yourself up if you stay consistent like this. But if you do another method where you constantly flip the directions of the arrows, you're gonna trip yourself up 100%. Because if you do method of joints, you screw up one calc, it's all wrong. Like all the following calcs will be wrong, right? Yep. Question.
So why is the arrow pointing to the left?
Oh, good question. So we're looking. Okay. So here's joint A, and here's where joint B is situated. Yeah. So when we're looking at particle equilibrium, kind of looks like this. Right. And if we want tension, we assume it's pointing away from the node. Let me move this fella. Because the equal and opposite reactions will cause the member to be pulled apart like that, right? You following? Yeah. So whenever, yeah, we just assume all the members are in tension that we don't know, right? And then if it's a negative value, it's technically in compression. But we just keep the arrows pointing away from the nodes. Yeah. Yeah. Okay, so now we have this one unknown which we solve for, EC, right? And this is in compression, all good, right? And then similar process, okay. Might talk about the sum in the y direction. So downwards 1 kilonewton force, and then we have these arrows pointing down, down, up, right? So this can be -1, minus BH, which is the one pointing straight down, minus AB sine 26.565. So that's the downwards arrow there. And then plus BC sine 26.565, right? But we basically found out that BC and AC actually have the same value, magnitude of compression. So we can literally, these cancel each other out, right? So BH is just going to be -1 kilonewtons in compression, right? Makes sense? Okay. So let's look at our next node. So now that we've solved this member, this member, this member, this member, right? Where should we go next? Should we go to C or should we go to H? Very good. Technically, you can go to C because of symmetry, but I would go to H. It's just simpler. And then when you get to C, it'll be really, really easy. Oh, and I should redraw the... Yeah, that's 0 force, right? So we don't consider that. But yeah, let's go to H. I prefer H. Because, let's look ahead. When we go to H, we don't even need to go to C at all. Because once we go to H, we'll tick off these last two members which we were missing. And the rest are either 0 force or done through symmetry, right? So H is actually going to be the last joint which we look at. Oh, actually, yeah. So just back to that. We could go to C, but then we need to find this member anyway. And there's no, it's just faster to go straight to H, right? Okay. So here's what H looks like. And we take the sum in the y direction first. So that's positive BH, positive CH, sine 45. So we're looking at the the vertical component of CH and BH. And BH will actually be a negative number, like that, right? Now we can work out for CH. Should be in tension, like that. And Fx, negative AH, that's that one there. HG and CH, the horizontal component, which is cosine. We're going to replace CH with the value we just found out. And we're going to replace AH with the value we calculated back when we analyzed joint A, right? So we really only have HG to solve for here, which will give us 2 kilonewtons in tension, right? Okay, does anyone have any questions? This question's finally done. The sections one won't take as long, but yeah. Does anyone have any questions about method of joints? Because that's the only method of joints question I'm going to run through today, that is. I would like to remind you guys as well that if you look at the folder, I've included the civil school workshops and the mining school workshops. So civil school workshops just has the solutions for what you've already been provided on Moodle. And the mining school workshops, I demonstrated this in the summer. I cherry-picked these questions from, actually that's a bad example. I cherry-picked these questions from the MEC booklet, and I've laid them out like this, and they all have solutions and stuff like this, right? So that's for beams. You might also want to look at workshop 3, which is the trusses. So the trusses are laid out like this. So there's a bunch of trusses to practice from. These are generally going to be harder than the ones you find in the civil questions, I feel. So these are good if you want practice. But again, the midterm will only really be as difficult as the civil school questions. So this is if you want the extra challenge and then dial it back for the midterm. Yep. Okay. So let's continue. Question 2. So here's the actual question and how it's presented, and then here I've redrawn it as a free body diagram. So the question asks for the magnitude and nature of the member BE, right? So BE is this one, and nature refers to whether it's in tension or compression. So which method should I use? Yeah.
Sections.
Very good. So as soon as it's asking for a specific member, right, that you can just cut through, there's no point in doing method of joints because method of joints is gonna, you saw how long method of joints took, right? You're gonna use the sections method. Okay, so this involves a few things. Firstly, how are we gonna cut across our structure to define a section? So you can't cut halfway through a structure and leave it like that. You need to cut entirely through a structure to reach from one end to the other, basically, right? But it doesn't need to be a straight line. So you can also cut like this, right? Or like this. Those are still perfectly legitimate cuts, right? We want to cut in a way that exposes the internal forces inside BE. So let's just do a horizontal cut. I might do it over here. So the next question is, which side do you want to look at, right? So once we've made our cut, we can look at all the forces above, or we can look at all the forces below. So logically, which one would you do in this question? Sorry? Yes, very good. Why is that? Exactly. Not only fewer members, you don't even need to solve for the support reactions. You know what I mean? It's gonna save you time, right? It's more efficient. Because the question doesn't ask for the support reactions. So that will be our section going up. I'm pointing the arrow up, like that. Yeah. Okay, I've included the support reactions, but in my notes I've written here, can skip for this question. Because our section cut points up, right? So this is actually what it boils down to, right? Our section. And this, like in theory, this will take less long than the method of joints, but there's a few tricks that you have to be aware of. It involves really understanding how the lines of actions work really well and how you can take some of the moments in the correct spot to get what you want, right? So again, let me just show. We care, at the end of the day, we only care about this member, right? And what its forces are. The other thing to note is that notice how I've drawn all of these unknown members still in tension, and if it's a negative number, we know that it'll be in compression, right? So basically, 9 times out of 10 with method of sections, you can't solve it. You can't solve it straight away using using your force equilibriums, right? You can see straight away we have diagonal forces, unknowns, and like all these things pointing in different directions, and there's too many to solve, right? So pretty much always we start with some of the moments. I specifically haven't written in a point yet. So the question is, which moment, which point do we take the moments about, right? And the answer is, I know the answer, but I'm trying to like explain why. Here are our lines of action, right? Let me just draw them out. Actually, I'll draw this one in orange. So this is the one we care about, right? Do you see how there's multiple points which these 3 unknowns intercept? So we have to choose the point to take the moments about that eliminates the 2 unknowns we don't care about. So does anyone want to guess which point it is we do care about?
You do it around D because
Yeah.
it cancels out
Very good.
B, C, and D.
Very good. There's no lever arm for the other two unknowns we don't care about. If we take the sum of the moments about BE, right? That's the whole trick with method of sections. Okay, so we take it about D, right? But we're gonna run into a problem. So we're like, okay, we're aiming to get this unknown, but lever arm is a perpendicular distance, right? That's this distance, right? How do I get that distance, right? Well, firstly, here's our angle, alpha, and it's going to look pretty familiar based on the geometry. So basically, it's a ratio of 1 to 2, right? So this number is actually going to pop up a lot in this course, or maybe not in this course, in the 1300 mining course. It's going to pop up a lot, but it's just this ratio of half, tan inverse half, and that's the same one we saw as before, 26.56 degrees, right? So firstly, that's that angle there, right? Okay, so how do we find out, let's call this lever arm D. Well, we can make a bigger triangle with this point which isn't even on our section. So you can still take some of the moments about certain points which are off our grid system, right, but are in the overall structure, right? So if we draw out this triangle, and because of similar triangles, this angle is also going to be alpha, right? Yeah. Hope you can see the relationship, but yeah, that's going to be alpha as well. And D is going to be, so here is 2 meters, 2 meters, right? D is going to be 4 meters times sine alpha, right? And again, that's 26.56 degrees. If we punch it in the calculator, that'll give us our lever arm that we care about. So that's the number we're going to plug in here, right, for some of the moments about BE. So the geometry is a little harder for method of sections, but overall calculations, you can see it's a lot less than method of joints, right? And I would say if you look through the midterms and solutions, generally they're going to want you to do method of sections. Yep. Okay. And then we also can't forget about our external loads. I might highlight them in red. These external loads, right? So that's, oh sorry, there's no moment for this load either, because we're taking the sum of the moments about D, so there's no lever arm. Yeah, so we just care about this times 2 meters, right? Okay, we can solve through our one unknown, and that's the answer to the question. So that probably took longer to explain than it actually does when you do the calculations, because it's literally like 5 lines of work. 2 lines are working, right? Or 3 lines are working, right? But yeah, does everyone understand that method? Yeah. Okay. So lastly, and I'm just going to run through this theoretically, because this is method of, oh, actually, okay, well, not to spoil it, but it says determine the magnitude and forces of each member for this truss system. So which type of method are we going to use? Very good. You're going to use the joints method because we want all of the members, right? Okay. The question also just straight up tells you, for the analysis, determination of the support reactions is not needed, right? So we can be smart about where we take our what do you call it? Our like we can be smart about which joints we analyze, right? So if I did this a long way, I can firstly work out these support reactions, right? And then I can start at joint. Can I even start there? I can't start there. Okay. Well, regardless, you can have start at these, right? But when you solve these members, right? Yeah. Okay. Okay. There's one more member in the middle, right? Okay. You know what? I'm gonna stop talking about it theoretically and just run you through the question. Our free body diagram looks like this. It looks a little funny because we have everything in newtons for its external loads, right? Oh, is anyone unsure about why this roller support is going to the right instead of upwards? Does anyone want to tell me why that's the case? Right.
It's just the convention is that usually you assume forces acting horizontally to the right.
Mm-hmm. That's right. Like what you said is correct, but remember with the roller support, it resists normal forces, but not tangential forces. So the fact that this is on a vertical surface instead means that it's free to move in the tangential direction. That's the way you want to think of it. Because what happens if it's on an incline? Do you know what I mean?
Right.
Yeah, you would have a different case, and then you'd have to have a better understanding of how these reactions work, right? Yeah. But yeah, no, you're completely right. Okay. Anyway, so if we look at joint D, right? Everything's vertical in terms of the member, in terms of the force, and when we take the sum of the force in the y direction, so it literally just ends up, as this in compression. So the reason is, as well, we assume tension, right? We assume tension pulling away from the node, and since we do that, and we get a negative number, it's actually compression, right? Is everyone following with that? And same with similar case of joint B, except this is going to be pulling away. One way you can do it based on vibes as well is like, here's the member, and this force is definitely going to stretch the member to some tension, right? Yeah, so we result in tension like that. Okay, so we can either choose, because we still need to get this diagonal member, we can choose to go to C or we can choose to go to A. So if we go to C, right, which is a roller, which has only one support reaction instead of two, we can actually avoid this support reaction entirely by taking the vertical forces, right? So that's like the little trick question. This is a super niche question. I wouldn't say it's representative of anything you're expecting to see in the midterm, but it's just teaching you that sometimes, even with the method of joints, you're not going to need to find all the support reactions, right? And you can still solve the question. Okay. Anyway, that's the end of the workshop. You're free to go. Yeah. And see you next week for the midterm. And good luck. Do you guys have any questions? If you do, feel free to come up front. I'm happy to answer them.